Dear students, I am Khondakar Fazlur Rabbi, lecturer, Milestone College, Uttara. Today we discuss about some creative question from first paper, chapter 3, periodic properties and chemical bonds. System is here given atomic number 6, 14, 15, 16, 17 and element E, F, G, H and R. Question number C. As per stamp between G and H, which has more ionization potential? Now we discuss about what is ionization potential. Ionization potential is the amount of energy is required to remove 1 mole electron from 1 mole isolated atom. An element in gaseous state is called ionization potential. Mainly, ionization potential depends on atomic number, size of atoms and electronic configuration. If we see in a periodic table, if we go left to right, the atomic number of element increases. So the attraction between the nucleus and the outermost shell electron is increases. As a result, to remove electron, the energy required more. So the ionization potential increases. If we see in a group, if we go top to bottom, the size of an element is increases. As a result, the ionization potential decreases. Now we see G and H. G atomic number 15, so the element is phosphorus, and H atomic number 16, the element is sulfur. Now we see the electronic configuration of phosphorus and sulfur. Phosphorus 1s2, 2s2, 2p6, 3s2, 3px1, 3py1, 3pz1. We see that the outermost shell electron is half filled. And if we see sulfur, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3px2, 3py1, 3pz1. That means the electronic configuration of the outermost shell electron is partially filled. We know that half filled and full filled electronic configuration is more stable than partially filled orbital. So the electronic configuration of phosphorus is more stable than sulfur. As a result, to remove electron from phosphorus, more energy is needed. So we can say that the ionization potential of phosphorus is more than sulfur. That means, as per the stamp, G has more ionization potential. Now question number D. Explain FR4 undergoes hydrolysis reaction but ER4 does not give hydrolysis reaction. Here ER4, E atomic number 6, so E represent carbon and R atomic number 17, that's why R represent chlorine, and F atomic number 14, so F represent silicon. So FR4 is silicon tetrachloride and ER4 is carbon tetrachloride. Now, if we see the electronic configuration of carbon and silicon, carbon is 1s2, 2s2, 2px1, 2py1, 2pz0, and silicon 1s2, 2s2, 2p6, 3s2, 3px1, 3py1, 3pz0, and 3d orbital is present. At first we write carbon tetrachloride plus water, no reaction. Silicon tetrachloride plus water, tetrahydroxy compound. Now, carbon tetrachloride is not hydrolyzed because carbon does not have any d orbital. As a result, it cannot form any coordinate bond with water. But in silicon, d orbital is present and vacant d orbital is present. That's why this d orbital, this vacant d orbital, can form coordinate bond with water molecule. At first, oxygen atom of water donates lone pair electron to the vacant orbital of silicon, vacant d orbital of silicon, and form addition product. At the second step, a molecule of hydrochloric acid is eliminated from the compound and a chlorine atom is substituted by hydroxyl group. The remaining 3 chlorine atoms are substituted by hydroxyl group, and thus a tetrahydroxy compound is formed. As a result, silicon tetrachloride undergoes hydrolysis reaction. So we can say that carbon tetrachloride does not react with water and silicon tetrachloride reacts with water. Now, stem 2. Electronic configuration of an atom AR n-1 d6 ns2. Question number C. According to the stem, this element is a transition element. Explain. So, what is transition element? The d block element which have partially filled d orbital in its outermost shell in the stable ionic state is known as transition element. So, the condition for transition element is the element must be d block element. D block element. The first condition. Second condition is for the stable ion, and third condition is electronic configuration is d1 to 9. That means partially filled d orbital. If any element follow this condition, that one is transition element. Now, what is the element? AR n-1 d6 ns2. AR is argon. So we write the electronic configuration of argon 1s2, 2s2, 2p6, 3s2, 3p6. This is the electronic configuration of argon. And n-1 d6 ns2. That means n-1 means 3 d6, and the last one n-1, that means n equal to 4 s2. If n equal to 4, then n minus 1 equal to 3. If n equal to 4, n minus 1 equal to 3. So total number of electron is 26. Total number of electron is 26. So the element is iron. So the element is iron. Now we see the stable ion of iron. There are two stable ion of iron, that is iron 2 plus and iron 3 plus. So electronic configuration of iron 2 plus is 1s2, 2s2, 2p, 6, 3s2, 3p6, 3d6. And electronic configuration of iron 3 plus 1s2, 2s2, 2p6, 3s2, 3p6, 3p6, 3d5. So if we see the condition for transition element, first one is d block element, second one is stable ion, third one is electronic configuration, D1 to 9. Okay, now this one is iron electronic configuration. This one is also d block element, because the last electron enter d orbital, that's why this one is d block element. And stable ion, iron 2 plus, partially filled d orbital, that means the electronic configuration is between d1 to 9. This one is also d block element, stable ion, electronic configuration, last d orbital 3d5, which is between d1 to 9. So we can say that the element is transition element. Now we discuss about question number D. How does the element forms complex compound? Analyze. The element means iron. Now formation of ferrocyanide ion. The electronic configuration of ferrous ion is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 and 4s0. Here 3p orbital is also present. According to Hertz's rule, we use box process. Electronic configuration 3d6, 1, 2, 3, 4, 5, 6, 4s orbital and 4p orbital. In presence of strong ligand cyanide, pairing occurs. That means these two electrons shifts to these two orbital and pairing occurs. And this d orbital now is vacant. This 2d orbital is now vacant. That means this electron, if this electron shifts to this orbital and this electron shifts to this orbital, then this 2 orbital became vacant. And here 2d orbital, inner d orbital, 2d orbital, 1s orbital and 3p orbital mixed up one another and form 6 identical d2sp3 hybrid orbital, which is vacant. And now the pair electron of cyanide form coordinate bond with this d2sp3 hybrid orbital and 6 coordinate bond formed. and that's why the shape is octahedral. This one is coordinate bond. If we see for ferrocyanide ion 3+, then the electronic configuration is 3d5, and for this case one electron shifts to this orbital, (3d5). One electron, this orbital, this electron shifts to this orbital, and pairing occurs. Here one unpaired electron present, but here also 2d orbital is vacant, and 2d orbital, 1s orbital and 3p orbital mixed up one another and form 6 identical d2sp3 hybrid orbital, and this vacant d orbital is form coordinate bond with cyanide. As a result, ferrocyanide ion form, and the shape of this ferrocyanide ion is also octahedral. Thank you.